Let's have a look at disk caching. So if we use a disk in a plain way, we have our disk over here, and then we have our program over here running in a processing unit. Now if we issue a read command to the disk will read the entry of the disk and return the data to the client. If we write something to the disk will perform the write operation and return the data, or return the success or failure back to the client. Now, when we issue a write command and when we issue a read command, the disk actually has to perform these operations. Now, of course, in modern disk solutions and when using a disk through an OS, there are multiple layers of caching in between. But we're here looking at the plain use of a disk device, where we issue a read command and it actually reads it off the disk physically. And when we issue a write command, it actually writes the data physically to the disk. So, in order to speed this process up, we can do something different. So, instead of talking to the disk directly, our client instead talks to a virtual disk. As usual, we write the virtual disk as a dotted disk. So our client program talks to the virtual disk, and the virtual disk is implemented by another processing unit that talks directly to the disk. Now, when the client asks to read off an entry of the disk, the read command goes to the processing unit, which then checks whether the entry is cached in its memory. If it is, it is returned directly back to the client. In this case, we did not have to do the actual physical read of the disk itself. When we do a write, of course, if the client wants to be sure that the write has actually been performed, then the virtual disk system must issue the write command before it can send back the confirmation that the write succeeded. Other disk caching solutions can, for example, return that the entry has been written and then schedule the write to the disk later. But this has the risk of not persisting all the writes that has occurred. But it will speed up the disk operations significantly. The program inside the cache here. So this is the cache and this is the main program. Now, the program inside the disk cache solution can choose between many different cache strategies. A very simple cache strategy that demonstrates how caching works is as follows. We can decide upon how many entries we would like to store in memory. And this depends on how much memory we have in the cache. For this example, let's say that our disk over here has 100 entries, and that we want our cache to store 10 of them in RAM at any time. So the cache maintains a table of 10 rows. So let's see, 1, let's add 2 more. Let's call this 0, 1. And then we need 2 more columns. So initially, the whole cache is empty. Then when a read command is issued, here, let's say we get a read command for entry number 51. So entry number 51. The cache then does a modulus on the 51 of on the size of the cache, which is 10, and the 51 modulus 10 is 1, it looks at row 1 and see that it is empty. So it performs the read against the disk itself. When the disk returns the data, the cache notes in its table that we have now cached entry 51. And here's the data. So let's erase some of the history here. So the next time the client asks for entry number 51, the cache will again do a modulus 10, get 1. It will look up in its table and see that yes, in entry number 1 we have cached disk entry number 51. So the data can be returned directly back to the main program. Now let's do another situation. Let's say a write command is issued to entry number 1. So write entry number 1. Again, when we do the modulus with 10, we get 1. But now we see that this entry is occupied by entry 51. So we will have to delete this entry from the cache, purge it from the cache. Then we write back, then we write entry number 1 here and the data here. And we do the write command to the disk itself. When the disk confirms that the write has been carried out, we can return to the main program. The cache strategy presented here is a very simple one, but it does show the basics of how a cache can work. Another nice benefit of this cache strategy is that it makes it quite easy to implement a complete memory cache. So again, if the total size of the disk here is 100, we can allocate 100 for our cache, which means that it can do a complete memory cache of the whole disk. A more sophisticated cache strategy might employ something called the least recently used strategy, which means that we track when the entry was last used, and then we purge from the cache the reads or the entries that are least recently used. For this, we would have to connect a clock device to our cache. So we take our clock device here. Let's have the right color. Clock device here. And we connect it to our cache. Now the cache can get the current time and note it in our table down here based on how the strategy works. Another thing that can be added to the cache is a high-speed disk. So let's say we have a high-speed disk solution here. If you connect that to the cache, then we can cache some reads and writes to this high-speed disk and then schedule the writes to the physical disk or the slower disk later. Disk caching is often used in multiple levels of a system. Let's have a look at how that often works. So for example, let's say we have multiple physical disks over here. And let's say that these 3 disks are combined by a RAID system with some error correction and stuff like that. Usually we get a disk cache in between, in front of each disk here, usually embedded in the disk device itself. Each of these present then a virtual disk. So they present the virtual disk. And then the disk or the RAID system uses these 3 virtual disks. Typically we get another cache then in front here. Which is provided by another cache sitting here. And then we get our client solution here. So the client can issue a read or a write command first to the cache of the RAID system. If it needs to read or write further information, it will go to the RAID system and then go to the disks here. But they might also be caught by the disk caches of each of the disks. And these kind of layers of caches are implemented to really speed up the operation of the system. Let's now look at an implementation of a cache program. Here we have an implementation in about 100 lines of code. The cache strategy implemented here is the modulus approach discussed earlier, which is a basic approach, but it does show some of the benefits of having a cache. First, the cache is initialized, which means that the memory required is allocated. In this example here, we will allocate a cache of size 10, which means that it will cache 10 entries. Then, as each operation comes in from the client, we will go through an iteration here. So let's see what happens. Now the first command that comes in from the client is, it asks for the size of the disk. And this is of course cached. In this example here, we have 1,000 entries of 1,024 bytes each. So the cache just immediately returns the size to the client. Let's see what happens the second time around. Now the client asks to write something to the disk. In this program here, the write will be issued to the disk itself, and then the confirmation will be sent back to the client. So first, the cache solution checks that the entry is within the range of the disk. Then it computes the position in memory where we will store the cached entry. The client here asks to write to entry number 950, and when we compute the position in the cache, it will be 0. So we get out the structure for the entry number 0. We copy the data into that entry. We note that it has been cached and the entry that has been cached. So if we look now in the disk cache, entry 0 has cached entry number 950. It is now in the cache, and here we have the data. Then we issue the write command to the disk itself and returns to the client. Okay, so the third round. Let's see what the client does now. The client now issues a read command to the disk. The disk cache then checks whether the read is within the range that the disk can handle. It is. It then computes the position in the cache where it might find the cached entry. And then it checks whether this entry has been cached. It has. And it checks whether the entry is correct. Let's see. Yes, it is. So now we can conclude that the entry is in fact cached. So now, instead of actually going through and reading from the disk, we can just skip that part and now simply copy the data that the client needs directly back to the client and then send the result back. If you found this video interesting and would like to learn more, check out the book Foundations of Computer Science, available on Amazon.